Okay, we're now going to continue to look at some more examples of interference of light waves. As you learned in the previous lecture, because of the special nature of visible light, in order to have interference, in order to meet coherence condition, you must take the same light wave and split it before you combine it again to form interference. You cannot have two different waves combining to get a stable interference pattern. So the way we split light waves before was we had the same light wave and then we just allowed it to pass through two slits or even more slits. But there are other ways to split the same beam. One example would be using reflection. Okay, so what I have here is something like this. I have a mirror and there is a light source, S, monochromatic light source with a single frequency. Okay, and I here have a screen here, and I wish to establish an interference pattern on the screen from this light source. Of course, a single source itself won't do it. So I need to split this source. And how do I do that? Well, I do that with the mirror, because this is only one way for the light to get there. There is another way. We call this beam 1. Okay, there is another way, and that is to get reflected from the mirror, which can also reach point P. So something like this. Okay, we call this pass 2. Because they came from the same source, pass 1, pass 2, they have the same initial phase. Okay, and then you can, from the path length difference, you can find whether you have a bright or dark fringe. Okay, so that's the idea. Now, we have to consider something special when it comes to reflection before we can move on with this problem. It turns out that when light reflects off of a boundary between two media, sometimes the reflected light will abruptly change phase compared with the incident light, and the amount of phase change is 180 degrees, which is equivalent to pi. This is called a pi phase shift. It doesn't always happen, but it sometimes does. Okay, without solving the Maxwell's equations, we cannot exactly understand where the pi phase shift comes from. But what I can do is give you a mechanical analogy. For example, I have a rope attached to a wall. Okay, now I send a wave down. Okay, send a wave down. This wave, when it hits this boundary, what happens? It bounces back, right? But when it bounces back, it doesn't bounce back like that, you see. Rather, it bounces back like this, right? That's how you form a standing wave. So you see, upon reflection, the original wave was like this. Now the new wave is reversed. You see, the oscillation is reversed. So here's a clear example of a pi phase shift. In a mechanical case, when the wave upon reflection acquires an additional phase difference of pi, that's called a pi phase shift. Okay, now in the electromagnetic case, an electromagnetic wave bounced off of a mirror does not always have a pi phase shift. Okay, this happens only if light is incident upon a medium that is optically less dense than a second medium. For example, if this is air, this is water, okay, then when light gets reflected off of the water surface going back to air, there will be a pi phase shift. Why? Because air is not as optically dense as water. In other words, N water is greater than N air. The index of refraction of water is greater than air. If this is water, this is air, then as water bounces off the boundary, as light bounces off the boundary and goes back into water, there will not be any pi phase shift. Okay, so the pi phase shift only occurs when this N is less. Okay, that knowledge in mind form an interference pattern with reflection. Now, to make the geometry a little bit easier, what I can do is I can find the mirror image of S. We call it S prime. Okay, it is clear because of the geometry that when I connect these 2 points, I'm gonna get a straight line. Okay, this is a straight line, right? Can you see that? It is a straight line because A, these two angles are the same. These two angles are the same because these two triangles are congruent, and B, those two angles are also the same because of the law of reflection, and then therefore C, these two angles are the same, okay, and therefore this is a straight line. Not only is it a straight line, this length equals that length. So that means x2 is really from here to there, x1 is from here to there. Okay? Now, what is delta x then? What is delta x? The path difference between path 2 and path 1. Well, assuming that s and s prime very close to each other. This is the assumption we're going to make. Okay? Otherwise, see, if the two sources are very far away from each other, they're not going to have interference at that point, even if every condition is satisfied. Why? Because think about it. Each wave, okay, really forms a train like this. And even though light travels very fast, this wave train is not all that long. Okay, this wave train is not all that long. It depends on what kind of source you have. If it's laser, it can be pretty long. But if you look at, just regular light source, it can be quite short, like a few millimeters or even shorter. And then, if these two sources are very far from each other, and then the problem is, this guy and that guy, these two waves may belong to different wave trains. And different wave trains, the phase difference between them is totally random, because when is each wave train emitted, that depends on the behavior of each individual atoms, which is totally random. So, in any physical optics device, when we look at interference, what you always see is that these sources are very close to each other. We're typically looking at the range of millimeters or less. Okay, so this is pretty short. And on the other hand, this distance can be a lot longer, can be a few meters, for example. So, we still have the same approximation that this angle is very, very small. Okay, and once you consider s prime and s, instead of the reflection, just say s prime and s, this resembles a two-slit interference, or double-slit interference, or Young's experiment, don't you think? Okay, the only difference is that the second wave has an additional pi phase shift due to the reflection. Okay, now without consideration of pi phase shift, if x2 minus x1 equals n lambda, what are you going to get? You can get a bright spot, right? Constructed interference. But what really happens is that the second wave now gets reflected, so therefore its phase reverses. So instead of going up simultaneously for both waves, one wave decides to go down because of the pi phase shift, and that changes the condition for maxima to the condition for minima. So originally you would have a bright spot here, now you have a dark spot. And originally if there were a dark spot, now becomes a bright spot. So that's all you have to do, is reverse the condition for constructive and destructive interference. Everything else is the same. Okay. The separation between the two sources is d. Okay, this is what we call d. It's twice the distance between the source and the mirror. Right, and this is y, and this angle here is theta. So I still have the same thing. The value of delta x, which is x2 minus x1, is still roughly d times sine theta. Right, d sine theta. That is still the same geometry. But this time, if delta x equals d sine theta, if that equals n lambda, you're no longer going to have a maxima. Okay, it becomes minimum, right? Because of the pi phase shift. It's the location of a minimum. On the other hand, if it's n plus a half lambda, that turns out to be a maximum. So these are the locations of maxima instead of interference minima. That is the only difference. Okay, so here's an example of interference through reflection.